and we're going to be speaking about the work we've done the past year and a half, 2 years. Quarterly statements. I'm now the guy liable, so there's a lot of grains of salt these days, so please take them before making any decisions. And as Dan said, the sport team above us are all colleagues, a long experience with each other, and a great team with a lot of experience in Nevada and globally. So it's been a real pleasure working with everybody and a lot of great guidance. And geologists, we've grown and a great team of and a bunch of experience in different deposits and systems that really contributes to a lot of sharing of ideas and new ones. So I'm going to go through this kind of in the sequence of how the projects came into our portfolio and how we've worked them. 4 projects that we have. First one is the Hot Springs Range project. This is just north of Winnemucca, up in the northern portion of the Hot Springs Range. Not to be confused, there's 3 projects in this range, but they all have roughly the same name. Ours is the Hot Springs Range projects, not the Hot Spring projects or the Hot Springs Peak project. Weepaw is to the south. This is just north of Clayton Valley and Silver Peak. Spanish Moon is over here in the southeast corner of the Tokima Range. It's on the other side of Mount Jefferson from Round Mountain. Then Gilbert South is in the Monte Cristo Range here just west of Tonopah. So, as Dan mentioned, this was kind of an idea bred out of graduate students probably talking geology way too much. I'd say we didn't have enough free time, but Gene and I were raising kids. But at the same time, it's really a passion of Gene and mine, and Luke developed some of these ideas out of discussions with our advisors and research, and our real goal was, can we use some of these new ideas coming out of grad school and things we're learning to find a target within Nevada that may have been overlooked. And the target we came up with was in the Hot Springs Range. And for those familiar, Osgood's come up here, the Getchell Trend, and just the north, the Hot Springs Range follows a very similar trend. And if you look at it, and this is something my team pointed out to me very early on in my PhD, because I love fractals, it's almost the same structural framework between these 2 mountain ranges. The biggest hang-up most people have is the geology. The lithologic units are significantly different ages between these ranges, but the lithologies are very similar. So in our kind of free time, as Dan was saying, well, I think Luke was full-time in school, just starting his master's, and Gene and I were trying to finish up. We kind of nucleated this idea and did a little of the initial field work and got the seed money to follow this up with a large soil program, mapping, and rock chips. The kind of real impetus for this for Gene and I is raising 2 kids, and both of us want to be geologists. It's hard to do that and keep the kids involved in the family. So this allows us to integrate our son and daughter with a lot of the work we do. So it's been a real pleasure. So we've taken this, as you can see, from a conceptual idea of just similar structural framework, nearby location, and this is some the kind of baseline geochemistries from USGS data sets that existed before this was discovered. There's a very similar geochemical footprint in these ranges. And we've actually, from the initial field work, we're able to identify decent numbers of gold on the surface in an area nobody's worked. Getchell Gold has their project north of Hot Springs Peak up here. Then Osgood Gold has their project in Dutch Flats, which I think is leased out to another company down here to the south. Almost the whole range is unprospective, but there's one small corner that we saw as being unique. And as Dan mentioned, it started with that project, and we brought 3 other ones into this company in the past year. And Jim and Dan have been great mentors. Something you don't learn in college is how to take a geologic idea that looks nice on paper and a map and turn it into something that is interesting to the market and sell it and develop it from staking it, developing the whole greenfield exploration program and getting it to the drill stage. And these guys have a wealth of experience. And to be honest, almost every valley we've gone into Nevada, Jim has been there before and knows the next outcrop. Nobody's more intimate with Nevada than Jim. So it's been a real pleasure to learn from both these guys, as well as recently Mark Coolbaugh has helped us an immense wealth of knowledge for Nevada. So what was the kind of concept that really initiated this? As everybody knows, I like figures. So this will be very figure-intense discussion here. So part of the ending of my PhD was putting into context the Northern Nevada Rift amongst the whole geologic history of Nevada. And it was a very end of the dissertation thing that I was instructed by my advisors to kind of compile. And that's when I made these sections. And sorry if it's a little fuzzy, but very simple schematic time sequence sections of mostly north central Nevada and going from a rifted margin to multiple orogenies and how we end up with the Northern Nevada Rift and these faults being great locations for veins. So on this slide, I'm going to integrate my thinking on that with work from Elizabeth Jones Crawford. If you're familiar with her work, she now is, I think, with the USGS. Originally did her PhD out of Berkeley on rock in the Golconda terrain. Her focus on this terrain was largely due to the Golconda terrain, and this is where occurs up in the Hot Springs Range as well as the Osgood and the Sonomas. This terrain is unique in that almost all the rocks are crazy exotic. They're not things that were being deposited out in the basin and being thrusted on. They're island arcs, all kinds of stuff that's out in the middle ocean, been accreted on. And a lot of the rocks are more similar to stuff that's up in Oregon than most things in Nevada. So part of the work that these maps come from is her compiling a list of all the different terrains in Nevada and how these things came to be through time as a function of different orogenies. And just for reference here, the strontium 706 line is what many, even though not everybody believes it, represents the rifted margin of Proterozoic North America. Everything to the west, shed off to Australia or Russia, and everything since then has been deposited on top, up top this margin, or accreted on from the east or from the west. So this all seems like a big build-up, but it leads to understanding why a couple of students can think one spot on the map see more perspective than others. So the time series, we'll go through this and kind of show the map version, the cross-section, and my brain just tries to put everything in some kind of 3D, and why this is significant. The kind of wavy line that we see in the 706 line reflects in the younger geometries of the different thrust fronts that come across. And what that's really being driven by is the irregularity of that margin and the major faults that would have formed kind of both transform faults along that margin, the big normal faults that more or less correspond with the axis of the Northern Nevada Rift. And up here, probably the biggest limit, the Snake River Plain transform fault that you could just walk all the way out to Yellowstone. And those are really the expression of these types of crustal scale features during that period in the Proterozoic. But through time, as you're thrusting things on top of that, the big takeaway I had in my dissertation is you're putting thrust on top of that, but you're actually probably what I call vertical accretion. You're causing reverse motion in these older rifted faults. You're actually propagating that structural fabric up through the crust as it grows. And the real geometry of that keeps getting inherited through time. Here's the Roberts Mount thrust. And you can get different maps of how these thrusts lay out depending on what author you go to. But more or less, they mimic the terrains that Elizabeth Jones has mapped out. Whoop, there's the big one. So up here in the northern portion of the state, the area that we're interested in, you actually have one of these large transform faults. You can get out there and go put your hands on. Most of the stuff you would say is kind of inferred, because almost all the rocks from here all the way to Yellowstone are underneath a bunch of young volcanics. You can just arm wave all day about it. You actually put your hand on these transform faults here in the northern Hot Springs Range. We'll get there, Doug. We'll get there. Sorry, I'm building up. So this is the kind of logic we were using at the time as a bunch of arm wavy grad students. And through time, this is the kind of idea that I had as well. Almost every major structural feature keeps following this drifted margin. This is the Paleo Divide from Pierce Henry. More or less corresponds to this. And that really formed during this time frame in this orogeny. Over to the east, you kind of see this as a big subvertical reverse faults, uplifting mountains in the Rockies. For us, though, you create that divide. Arguably, you're uplifting this portion and create that Paleo Divide. It's probably not coincidence that immediately prior, the Central Nevada thrust belt, as described by Sean Long, corresponds to that same axis. You're actually causing these reverse faults to reactivate and propagate these faults up through the younger thrust range. So got down to it, I ended up here. None of my research is, well, the Northern Nevada Rift sits right there. And the youngest episode of major technism is the downdropping and the reactivity of these reverse faults back to normal motion. And some of the work, Jeet's advisor Mike Russell and his PhD student Elizabeth Hollingsworth was on the southern Carlin trend and recognizing that you had Carlin fluids coming up into the bottom of Eocene age basins, and gravels that were previously interpreted as Battle Mountain Formation were actually basal gravels in these basins forming during the extensional setting of the really early portion of basins forming along this axis. So we knew to look for those. Then my time frame is, well, those same things get reactivated in the mid-Miocene when basin range extension really kicks off. So the main feature for us was finding a place where you had those faults active, the rise host rocks available, and stuff wasn't staked already by the major companies that seem to have, the majority of the land. And the one place that was available was up here in the northern hot springs range. So now we'll take a look at that. So this is the very northern portion of the hot springs range. Eden Valley, for those familiar out there, is just out here to the southeast. Little Humboldt River comes snaking through here. If you ever gone to the hot springs, they're right up here, right next to the river. The unique thing about this part of the world that most people would overlook, but if you're familiar with me, all I look at are basalt. I've been doing so since I did my master's. All these red rocks are mid-Miocene basalt. Not usually what you look for in an Eocene age Carlin deposit. And they were mapped by Elizabeth Jones. What she didn't map, though, is on the very edge of these, where you have exposure down to the Paleozoic tertiary contact, are Eocene age gravels, tufaceous sediments, lacustrine sediments in some spots, suggesting that these western margins to this basin was tectonically active during the Eocene. And the real neat thing here is you have this northern margin of the basin following this kind of orientation as well, suggesting that was tectonically active, creating this depot center. You see thickness changes of the basalts across these structures. One of my favorite relationships, these are growth faults. They were actively rupturing during that time frame. And the best part, going to Don's question, is the rocks. Almost all the hot springs ranges of Harmony formations, the south all the way to get to the Dutch Flats area. Not a great host rock for Carlin gold, Carlin type gold. But as you can see, the contact between Devonian Harmon formation and stuff to north, 10 perm rocks, is almost a perfect strike slip fault that moves along this northern boundary, and you can literally just walk across this with one step. And this is one of those tear faults that was on one of these thrust fronts. Probably overlooked. Elizabeth Jones was super interested in these types of features because a lot's going on in a very small footprint here. So you go from the Devonian to Pennsylvanian phyllites and shales. Then you can see there's a very small thrust here. This is part of the home ranch terrain. And the only place you're going to find the home ranch terrain is here, right next to home ranch. But this is part of the Golconda lock fund. You're actually thrusting Mississippian age limestones and andesites on top of the phyllites. And they're significantly younger than the Comus formation, but almost the same kind of geologic environment, paleo environment. They're a, help me out. Comus formation is a seamount environment. You can go out there and find outcrops where you have chilled class of andesite sitting plopped down into limestones. So a seamount environment, no different than Comus formation, just a little bit younger. Then go to the northern boundary of that. There's another one of these strike slip faults that puts the Mississippi right next to the Poverty Peak Permian melange. Then another one of these, and they're all subparallel. So you can imagine these things are thrusting on, accreting on. They hit an abutment down here, but then just to the north, you move into that Snake River Plain, and they slide along. And these large subvertical strike slip faults, you're putting the Jurassic right next to that. So significantly large, arguably crustal scale features. And what we recognize is, well, the basin margin of the tertiary age basin is exploiting and reactivating these strike slip faults. You're creating a permeability pathway on a crustal scale, and it's laid out right there from mapping that Elizabeth Jones did. The big thing for us was going out there really defining the tertiary age faults by offsets and displacements of the volcanics and the sediments underneath. So that's where we got to this cross section going from west to east. The tough thing here is you do have more post-mineral cover, being the basalts and the sediments than the quaternary alluvium. But the neat thing is, since these are strike slip faults, the strike of the cross-section matches the kind of strike of the contact between the host rocks. So you can follow the, arguably, we won't know until later this year, but the same home ranch terrain should persist along strike. And that's what the geophysics suggests to us and what we infer in this cross-section. So our Otis target is over here to the west, where you have a intersection, dilating intersection between the northwest fault and the northeast. Then over here is our Eden target, this one here. Similar intersection out here, but just blind. Only thing preserved the surface here is Miocene basalts, but arguably the same host rocks and thrust system should exist at depth. And yeah, so yeah, I simplify these. Yeah, red here is now, I kind of make this an easy correlation, just yellow. So quaternary and tertiary units are all this yellow thick package. So that's the Miocene basalt on top. I do that because it kind of corresponds better to this section. Down in the Getchell Trend, you have similar package of rocks. They're just a lot thinner. You can see out here just to the east of the Twin Creeks. In Vista Pits, you got a skiff of this tertiary stuff on top as well. And even parts of it right above TR. Just not talked about because the deposit was exposed. But the neat thing is, sorry, I didn't mean to kill that. The footprint of mineralization over here, if you look at the up-dip portion of the BBT fault and the TR corridor fault, has very similar numbers to the up-dip portion we're seeing exposed the surface out to the west. So very intriguing, albeit most of our targets are blind due to that thicker tertiary cover. This is zooming into the Otis area. So the intersecting faults, northwest ones, these are equivalents, would be the Getchell fault, and that whole fault system that goes along the eastern side of the Osgoods. Similar structures here, east dipping, steeply dipping, normal faults bounding that basin margin. Section from west to east here is this one here. And what we have is the exhumed footwall, within the footwall of that basin, is where our real geochemical anomaly is occurring. So we're really bringing this system to surface, exposing it. What we really have is anomalous soils and rock chips that cover everything due west of where our inferred target is, where those faults intersect. And this was conceptualized early on, and going out and doing soils and rock chips, validated by actually having numerous rock chips along that thrust front, giving values up to 0.7 ppm. One of the earliest rock chips Luke actually took when he was actually staking and just had a keen eye. That's a half a kilometer right there. So we're getting, 0.7, 0.4, almost a half a kilometer, 3/4 away from the kind of target area. And the idea is that's vertically coming up one of these feeder faults and laterally following out that thrust plane underneath the home ranch terrain. There were stakes somewhere in the early 90s, I think. We found a couple. So that was very rewarding having that. Then most of this actual fault is obscured by talus and stuff coming off these basalts, unfortunately. But where you do get little pieces of it poking through, we get better numbers along these kind of inferred feeder faults up to 2.8 grams per ton. And then we were able to do CSMT just this last year. This kind of conceptual structural model was very rewardingly kind of manifested in our CSMT lines, showing these east dipping faults that up to that point never been mapped by Elizabeth Jones, antithetics coming into them and down dropping this thrust along that fault. And the neat thing is you actually can map this inferred thrust contact and follow that CSMT where it daylights all the way out here. So we're pretty dang confident that that thrust is being down dropped. And if you're familiar with TR, our fellow student RJ, who just finished his master's on TR today, very similar geometry that we have at TR as well. This is Eden, slightly more difficult problem to kind of verify and convince people that the idea was valid, largely due to a thicker package of cover above it. So this section goes right along this D to D prime, upwards a couple hundred meters of quaternary cover and tertiary material. But the method we did here was kind of newfound. We did LiDAR, very high resolution surface mapping of this. I think it was like a foot resolution. Sorry, I was using a third of a meter, give or take. And map the quaternary faults. It doesn't seem that interesting because there's quaternary faults all over the state of Nevada. Well, if they're occurring in the right place, can be proved very valuable. Neat thing out here, again, while we're out staking, identify there's mud volcanoes that are localized just along these intersections right here. Mud volcanoes, we've been up to Bora Peak in Idaho, following that rupture in the 80s, liquefaction of the basin, fluids within the aquifers, down through the basin, all rushed up along fault scarps, brought water to the surface as well as geochemistry. So we did background soils across both the quaternary alluvium and the tertiary basalts. Background gold values was all below 1 ppb. You go along these scarps, you actually get relatively anomalous gold, as well as other pathfinders. Key ones being like selenium, which suggests there's sulfides at depth that are being scavenged, and that geochemical footprint being brought to the surface during these rupture events. So we were convinced to do CSAMT across that, found very similar down dropping of our inferred thrust fault, suggesting this fault was active well before the quaternary, kind of fitting our model, and it's convinced us to go drill test this next spring. So very exciting to see this go all the way from kind of concept to this stage in the past 2 years. Other projects, moving on. WEPA, this is again down north of Clayton Valley. Yeah, go ahead, Dave. Oh, I should have this number off the top of my head. It's a couple of thousand hectares. It's a big area. Yeah, all unpadded. We're just north of the checkerboard, conveniently. And yeah, it's about 10K across between the two projects. Yeah, no problem. So there's a real number on the webpage. I'm not good at memorizing things. WEPA, slightly different type system. Those familiar with that area, WEPA was historically discovered as a mine, underground mine, early 1900s. It was the first open pit. We went in there with a bigger picture idea. Let's really see what's controlling this historic mine mineralization. The mine itself produced along a similar type mineralization as Mineral Ridge, which is just to the south across the valley. Mesothermal bull quartz veins cut up with a shear zone that's interpreted to be part of low angle kind of detachment faulting in that part of the world. So we did a broad soil survey and kind of look at the region as a whole to see, are these detachments mineralized everywhere, or is there something else that could be influencing mineralization? And just get a bit of bigger stroke idea of what's going on. Oh, right. See, this is where I'm not good at memorizing numbers, Don.
40 by 40 by.
And we sample both bedrock exposures. And another feature that's down here, which I'm sure everybody's driven down through this region, is a very thick package of basin fill that kind of predates most of Walker Lane, the Esmeralda Formation, that fills in these valleys and is upwards of like 8,000 to 9,000 feet thick. Most of it's to the south, and that's the kind of formation that they're producing the brines out of for lithium. But up here in the WEPA Hills, there's small intramontane basins, and they obscure a lot of the bedrock geology and immediately adjacent to this historic pit. So we did pediment sampling on top of that using ionic leach with the real goal to see if there's any geochemical footprint coming through that pediment. And the kind of framework we came away with after mapping and doing the geochemistry was not only is this mesothermal shear veins, or what's influencing a lot of the structure here and utilizing, reactivating some of the older structure is just simple Walker Lane tectonics. Forming that intramontane basin is a very simple pull apart system, and those faults are being reactivated. And then this is, again, my brain. I try to 3D things before we get to the leapfrog, understand what's going on. The historic pits are right on the edges of this pull apart basin. And here's a cross section going from here southwest to northeast. Most of this region is covered with a thin veneer, a couple meters up to maybe 10 meters of gravel. And that's what they actually discovered the deposit from, was placer gold within that gravel. They just walked up the hill to the outcrop. And we zoom in, we've taken that concept understanding that there's two really ages of mineralization here: older mesothermal bull quartz veins and younger systems being controlled and influenced by these Walker Lane tectonics. And through relogging, Jim, Luke, and myself, and mapping the pit, identified younger brittle structures that influence mineralization and kind of upgrade what was mined in the pit. So it's opened up a new target potential for us well outside just these bull quartz veins and detachment faults. These large strike length portions of these basin bounding faults that were never really gone after by the historic workers because they're covered up with veneer pediment gravel. I didn't point that out. Do have a large arsenic anomaly along the margins of them. And were overlooked during the 1980s when they opened pit just along that shear zone. Oh, my bad. Then just recent work we've done has gone back in, Luke, using a lot of his underground mapping skills, map out the individual structures within this pit. So the main bull quartz vein shear zone that was mined is this kind of opaque color going along the axis of the pit. The head grade coming out when they were mining this in 86 was roughly 5 grams per ton. You can see the red are high angle structures mineralized. Most of them are on the footwall side. This thing dips to the west, and these are all part of one of these major strike slip faults forming that pull apart basin. And they are strongly mineralized, and the fluids that are coming up them are actually flattening out along low angle structures within that shear zone and metamorphic rocks. We're actually creating two mineral systems, one that's dependent upon the bull quartz veins and one that's more in line with the pull apart basin and kind of Miocene age tectonics, creating a whole new target for us. So it's been real exciting, and it's been kind of verified again. I kind of go back to all of our fellow graduate students. While I was going there, Mike Claypool did his master's on Mineral Ridge and identified a lot of the age of activity there was mid-Miocene as well. So the regional geology is supporting some of our observations. So I'll hand it over to Luke to speak on Spanish Moon and Gilbert South.
All right, so moving on to our next project, Spanish Moon. It's located in the southern end of the Toquima Range, just north of the town of Belmont, if you're familiar with that geography down there. And the project sits kind of sandwiched between a couple of plutons here, the Round Mountain Pluton, which just on the west side of that sits the Round Mountain Mine, and then the Belmont Pluton. And on the south end of that, southeast end of that, sits the Belmont Mining District. And this area is kind of, as a whole, is kind of riddled with deposits. You have Round Mountain, Gold Hill, Jefferson Canyon, Corcoran Canyon. Those are all epithermal deposits. And then on our land package, we have the Barcelona deposit, which is a mesothermal silver deposit, and then the Belmont deposit, which is also a mesothermal silver deposit. So there's been some really extensive mapping done by Dan Shaw and the USGS in this region, and it's really helped us out a lot. He's compiled 6 quad maps, and this really detailed mapping has been able to focus us in on a lot of the geologic features here. So like I said, at the eastern end of Spanish Moon here is mostly our mesothermal silver mineralization. It's a lot of tetrahedrite hosted in bull quartz veins, and we have some really high grade silver anomalies and rock chips there. But as we move to the east across the project area, and when we get into this Antone Canyon here, it's more of a gold focused system. Again, probably likely mesothermal related to these intrusions and the metamorphism in the Paleozoic host rocks here. Most of these host rocks are limestones, which have some silicification in them, and they're kind of butted up against a series of schists down to the south here. All this green on the map. So Antone Canyon, there's been some drilling on the east end of it, and has some pretty high grade drill intercepts. There's a north-south fault that kind of separates the east part of Antone Canyon from the west part of Antone Canyon. On the western portion is totally untested by drilling, and we have some really high grade rock chip samples across this east-west trend here. some 8-gram, 10-gram rock chip samples. And so this is a really exciting and prospective drill target for us here. And we call this the Hooper area after this. This was the old mine by the name of Hooper. Moving further to the east in Antone Canyon, this is the portion of some really good drilling here. We're going to focus in on this hole here, AC99-2. It had 13.8 grams over 1.5 meters. And this is what the drill core looks like. A lot of small quartz stringers and really dark carbonaceous limestone within the highly mineralized zone outlined in red. And acquiring this core had really been helpful for us to really see what the mineralization looks like, because these carbonaceous limestones don't outcrop very well on the surface. So this would be a similar, we'd be hoping to see these kind of rocks when we go drill at the Hooper area. Moving even further to the east in the project area, we have another kind of gold mineralized area here. It's in this area we call the Flowers Mines area, because there were 2 mines here, a mercury and an antimony mine back in the day. And we have some kind of rimming the north edge of this area. We have some over gram per ton gold and rock chips there hosted in the quartzite formation. And on the southern end here, we have a really big arsenic anomaly that we identified with soil sampling. And this arsenic anomaly is associated with some dickite that we've identified with some spectral, some infrared spectroscopy, and also that mercury antimony. So we're kind of thinking this area has more of an epithermal influence to it as compared to the rest of the more mesothermal type mineralization. So while there's not really high grade rock chip samples here on surface, you're trying to think about, well, where is this anomaly coming from? It's obviously, this is a high level expression of it. Where could we find a good epithermal target in this area? And this kind of led us to our next idea, where this is a little bit small. I apologize for that. But again, this Dan Shaw, he did this amazing mapping and took tons and tons of rock chip samples throughout the entire southern Tokemas. And he identified a lot of arsenic anomalies in the southern Tokemas. One of them sits in our Flowers area, and he even had rock chips outside of that area that kind of extended this arsenic anomaly kind of around the margin of the Jefferson caldera. But if you see here, there's a big arsenic anomaly on our property. Corcoran Canyon has a nice arsenic anomaly. Obviously, Round Mountain does. Jefferson Canyon, another epithermal system, has this arsenic anomaly. And a lot of this arsenic is just focused around the edge of the caldera. So it made us think, well, let's look up north a little bit and let's explore this caldera margin. When we dove a little deeper, we found more maps from Shaw really outlining the margin of the Jefferson caldera here. And this is sorry, I should have mentioned, this is a magnetics map, and it shows really well the margin of the caldera. And then there's some faults coming off of the caldera right on the northern edge of our of the Flowers area. So we think there's a big epithermal target here right on the southern edge of the Jefferson caldera, right at the intersection with this Meadow Canyon fault. And so here I've just outlined in red the margins of both the Manhattan and Jefferson calderas, and then some of the range front normal faults and normal faults that are coincident with the caldera margins. If you can see, there's a really striking similarity between the geometry of this Meadow Canyon fault that comes up the north end of our property. And then also there's another similar fault on the Manhattan caldera that's in the same structural position. And that's where all the mineralization in the Manhattan mines area is. Yeah. And the other similarity that we have is that there's this Meadow Canyon fault is juxtaposed along this north-south relay fault here, and it actually steps over. And at Round Mountain, they have a very similar step over geometry, which is also coincident to their little Round Mountain caldera out in the basin here. So if we put everything together, we zoom in on this a little bit more. I'm just highlighting the similarity between Manhattan and our Meadow Canyon target. Now, the only difference between like Round Mountain and Manhattan is that there's no cover rocks in these areas. Here in Meadow Canyon, we have a lot of Oligocene cover rocks that is younger than the mineralization at Round Mountain and at Jefferson Canyon. And we're thinking it's probably Oligocene mineralization here. And so we're getting little bits of that arsenic anomaly kind of peeking out on the edge of this. But once we get into the volcanic cover rocks, we're not seeing much. So our next step here would be to do some geophysics and maybe some soil sampling to see if we could extend this anomaly further to the north, and then hopefully look at drilling this Meadow Canyon target. So our final project is Gilbert South, and this one's in the Monte Cristo range that's west of Tonopah. This is our land package at Gilbert South, and we're just south of the old Gilbert town site and the McLean pit. So the geology here at Gilbert South is a lot of volcanic rocks. And in the heart of our property, we have rhyolite dome here in red, and then we have these outcrops of Paleozoic rocks. Probably the Palmetto Formation is what it looks most similarly to, and some of the USGS mappers have proposed it's the Palmetto Formation. These rocks are really messed up, so we're not exactly sure if they are Palmetto. Another striking feature of the geology here are these large-scale faults, which kind of bound these Paleozoic blocks. And one of the proposed theories by Aldau in this area is that these faults are in kind of making a pull-apart basin geometry on a right lateral strike slip fault, and then you have this low-angle detachment on the west side here, which is exposing these Paleozoic rocks and would make a really good source for upwelling fluids, and which we see because there's a big rhyolite dome right there. So one of the first things that we looked at here was we got some spectier data, and we identified a pretty extensive ammonium anomaly. If you're not familiar with ammonium and ammonium illites or smectites, it's just the ammonia gets trapped in the structure of these illites as alteration is forming, and usually like it happens in epithermal systems or in Carlin type systems, and it brings up the signature of the ammonium from basement rocks, and it traps it in the illites or smectites. Or another mineral is a feldspar called Buddingtonite that we see the ammonium in. And around the world, it's been associated with gold, very closely with gold in a lot of deposits. This one's at Favona down in New Zealand, and there's a nice ammonium anomaly right around their vein set here. So bring it back to Gilbert South and ours. All these blue dots on the map are where we went and used a handheld Halo ASD gun, and we identified spots of ammonium. And kind of these blue blobs here are the general trend of this. And so this is kind of gets us thinking about where possibly the fluid upwelling zones are along one of our main structures. So a main structure that we have in this area that we think is focusing our mineralization is called we named it the Pretty Boy structure. Coincident to that, we have the eastbound fault, and then on the west side, we have this Bighorn vein. We have some really high-grade rock chips along these structures, a few over 30 ppm along Pretty Boy, and same with this eastbound kind of intersection with Pretty Boy. And you can see on the last map, there's a huge ammonium anomaly right at the intersection of these faults. And then again, just along this Pretty Boy corridor. So this was really focusing us into that area. So kind of a cross section, our conceptual model of what's going on here is that on the west side here, we have this detachment surface, which is on the west side of this little pull apart on the right step across these strike slip faults. And then as we move to the east, the faults become a little bit higher angle, and we have this big pretty boy structure, which is on surface is just exposed as kind of a swarm of veins and a lot of stock works. But at depth, we think there's a really big potential to have a nice bonanza grade epithermal vein, especially since we see rock chips of like 30 ppm just running around on surface. So we also have a really good soil. We did a 100-meter isometric soil grid out here, and the soils, some of our highest grade soils are along this pretty boy fault corridor, and then again the Bighorn fault corridor. And really they're outlined in blue here. These Paleozoic rocks are really anomalous on the soils too, as well as the rhyolite dome. And so these are just some photographs of the mineralization that we see. Some really nice chalcedonic vein textures, some weird spheroidal chalcedonic and quartz vein textures, and then some nice banded veins that we saw in a mine adit underground there. And this was also a neat thing we saw. There's a lot of tuffs in the area, and this was a piece of charcoal that was preserved in the tuffs. So there are trees and stuff grown there in the Miocene when that tuff was deposited. So kind of when you put all this together, and we have these kind of high grade rock chips on surface and these stockwork zones, we think we're just right at the top of the boiling horizon in this system. And the old timers that mined here, they kind of just scratched the surface and they never really went that deep. And we're thinking that if we go a little bit deeper here, there's a really good potential to find a bonanza vein, especially with that big ammonium anomaly, great rock chips everywhere. So with that, I'm going to hand it back over to Justin to wrap up our presentation for the night. Thanks, Luke.
The end of the marketing presentation. As you can see, we're very early stages of the company, got our 4 projects together, and our next big step going into the next year is to go test all the ideas we've generated from field work. So exciting time for all of us, and happy to finally share it. Something we've all been kind of working on in private for the past 2 years, so a lot of fun. But yeah, happy to take any questions. Thanks, guys.